Hello everyone, my name is Quentin Bramas, and I'm going to present a joint work with Arthur Roche, Stéphane Devine, Pascal Lafourcade, and Anissa Lamani, which is basically about how to explore a finite grid with simple robots that have limited visibility and that are totally disoriented. So first about the model, as I said, we are going to look at robots that are moving in a finite grid. So here you see the nodes of the grid with the edges which represent how the robots can move between the nodes. And the outer limit of the grid are represented by black nodes, which we call the walls. Okay, so only the white nodes are the nodes of the finite grid. So as you see, robots have colors, which we sometimes represent just as letter. So here we have the L robot and F robot. Colors are simple states that can be seen by other robots and by robots himself. So they can be used as a kind of communication and some kind of memory. So robots are synchronous, so they synchronously execute some cycles. So first they look at their surroundings. So you can see here in the global configuration, robots only see what the state of the nodes at distance 1. So the L robot sees the F robot and the F robot sees the L robot. So they obtain this kind of view where they see the robots nearby at distance 1. And from there they compute a destination. So for instance here the F robot will decide to move towards the L robot, and the L robot will decide to move away from the F robot. So this is decided by the algorithm, and then they actually move to the destination. So here they reach this configuration. So except from the light with different colors, robots have no additional memory and no communication mean. And also we require that two robots simultaneously cannot occupy the same position. And also they are disoriented, which means that they don't have a common north. So when they look at their surrounding, they actually the view that they have actually can be rotated arbitrarily by an adversary. So they cannot distinguish between the four views here. So if we apply the algorithm in this global configuration, what will happen is that the group to the left will move to the left and the group of the right will move to the right, because the same rule will apply in both situations. Also, in this paper, we assume that the robots do not have a common chirality, which means that they cannot distinguish the left to the right if the view have an axis of symmetry. For instance, here the view has an axis of symmetry, and so the robot cannot distinguish between the left and the right of the configuration. If we decide to move to this node, then the adversary can mirror the view, so that in the end we end up in the other side of the view. Okay, so what's an algorithm? An algorithm is just a set of rules that defines for each view what is the destination. And we also so the algorithm also defines the initial configuration, okay, or the set of initial configuration. For instance, in our case, we will see that we will ask the robot to start in this with this shape, with 3 robots aligned and 2 robots with color L and 1 robot with color F. And this group can be placed in the grid regardless of its position. As soon as it respects its relative position and color, then the algorithm will work. Okay, so now what we want to solve with this kind of robot, in this paper we solved the perpetual finite grid exploration problem. So we start with a predefined initial configuration in the given grid, or in any given grid, and we want that each node of the grid should be visited by at least one robot infinitely often. Okay, so what we obtain? First, we obtain an impossibility result. So we show that with only 2 robots having visibility range 1, regardless of the number of the colors, the problem cannot be solved. And then we provided two algorithms, one which is optimal in terms of visibility range and in terms of the robot, because it has the minimum number of robots for the problem to be solvable when the visibility range is 1, so only 3 robots. And then we also showed that if we take robots with only one color, which means that they are oblivious, they don't have memory or communication because there's only one possible state. And then with visibility range 2 and only 5 robots, we can solve the problem with algorithm 2. So now I will first talk about the impossibility result and then show the algorithm. So first, to prove the impossibility result, we want to prove some lemmas. So first, we can see that if robots are far from the walls and execute a sequence of non-ambiguous moves, then they can only move in straight line. Okay, this is true because if robots move in an unambiguous manner, which means that since there are only 2 robots, the view must have an axis of symmetry, and non-ambiguous moves only allow them to move away from the robot or toward the robot. So they must remain on the same line. Then we show that if robots are far from the walls and execute a periodic sequence of movements containing an ambiguous move, then they are stuck in a loop. So to prove that, we can see that every time a robot executes an ambiguous move, the adversary can decide on which side of the line the robot will end up. So we can decide, for instance, to make a turn on one side. Then, since it's a periodic sequence of movement, the robots will make another ambiguous move, and so we can decide that they turn on this side. And then doing so, we can make sure that they end up in the same position. And so they end up in the loop and never explore the grid. So as soon as they are far from walls, they can only execute a sequence of movements that are non-ambiguous. And by doing so, they move in a straight line. So then there is a small lemma that says that if robots are on the same line, L, then the adversary can decide on which side of the line robots will move out of this line. And then to prove the theorem that says that the problem is not solvable with only 2 robots having visibility range 1. So to prove this theorem, we assume that such an algorithm exists, and we can see that at some point the robots will end up in a corner box, which is a box at the corner of the grid. And when the robots will move out of the box, 2 cases can happen. Either they will move in the same line until they reach the opposite wall, or they will make a turn, end up in the line L, and either enter the same corner box, or will move out of this rectangle from this side and move in a straight line until they reach the opposite wall. So in the first case, robots remain close to wall W2, and in the second case, robots remain close to the wall W1. And in both cases, they can end up in another corner box, and the same thing can happen again. So they will always remain close to a wall, which means that nodes in the center of the grid will never be visited. A contradiction. So now I will show the algorithm. So the algorithm starts with this configuration, and now I will play the entire algorithm to see what happens, and then we can discuss about all the specific different moves that happen in the execution. So you can see that, okay, I will look at this. So you can see that robots explore a line and that move out, and then here we have a turn and we explore a column, and then a column, and then move right, and then the column. Okay, so this is the pattern of the algorithm. And so you see that every time, if I click on, okay, maybe I have to do this. If I click on the robot, you can see that, for instance, here you have the view of the robot. So here the L robot sees an L robot to his left and a F robot to his right, which is the robot in the middle. And in this case, the algorithm say that you move to the left and you keep the same color, L. That's why you have an arrow here toward the left, which means that the robots will move to the left. And when one robot reach the wall, you have a rule that says, okay, when you see the wall in front of you and you have an L robot behind you, then you move along the wall, so here down. But since the configuration, the view is symmetric, then here the robot cannot distinguish between up and down. That's why you have two rows here, and the adversary will decide on which side. So here it doesn't matter which side is chosen by the adversary because the algorithm will succeed. So for instance, if the robot moves down, then we have some rules again that allow the robot to perform a small turn, and then the robot will move in a line here. So you can see here that in this configuration here, regardless of the size of the grid, the robots will move in a straight line until they reach the opposite wall. And then we have some rules that make them turn around, and regardless of the choice of the adversary, the robots will turn around and keep the same configuration here, but rotated by an angle pi, and we have like this. And here, when we reach the wall, robots will make a turn, but will end up in the line just above. Okay, so that's how the grid is visited. So I will just quickly show some rules. So here we have the rules that make the robots move in a straight line from one side and for when they come back. Then we have some rules that say that if we are in this configuration in the wall in front of them, then after some round they will end up like this. So we see the turnaround when they see a wall. We also have some rules that say that if we are in front of the wall and there is a robot here, then the rules will make sure that the robot will turn around, but in the line just above. So in the end, what the robots will do is that they will visit the line, come back, and move to the line above and do the same. So the grid is visited like this, and then we have some rule that say that they have to turn and now visit column. And that's how all the grids are visited. And then we'll end up in the same configuration as in the beginning, and so we can continue. Okay, so here again is the algorithm, so we can see what I was saying. The turn, then the up and turn, then the turn again. Then here we are at the corner, so we change the direction, and we now visit on this with this direction. And then we keep the same column, and then we change the column like this. So we also have different configuration, for instance, for different starting configuration, just to check that the algorithm works regardless of the initial position of the robot, and also that it works with in small grid. So you can look at all the example on my website. For the second algorithm, so robots here are all red, so they all have the same color. The principle is the same, so robots stack like this, and then we have this, and the goal here is to, when we are in front of a wall, to make a turn. But here actually we started by looking down one row and then turn around. So you can see here what happens. So they have the same configuration as before, but mirrored, so they move on the other direction. Then we have some specific sequence when we are close to a wall, and then we start on the other side. So now robots are moving up and the same thing happens at the top. Okay, so what we obtain is an optimal perpetual finite grid exploration algorithm with a finite number of disoriented robots with limited capabilities, small visibility range, few colors. And now for future work, what we want is to actually look at solutions for the asynchronous case. Thank you for your attention, and you can look at the slides in my website, bramas.fr. Thank you.